Pulsars emit mostly in the radio. In the radio, we can detect objects that are much cooler, like the pulsars that I studied. I'm Joanna Rankin. I'm a professor in the physics department of the University of Vermont. Some of those big, bright, massive stars, when they die, they undergo disruptions in which the mantle of the star is ejected with great velocity in something called a supernova event. And what's left is a cinder, which is a black hole or a pulsar or a neutron star. These pulsars are a very late stage in the evolution of stars. They're about the size of a city, but they have as much material as the sun, so they have enormous density. If I reach down to pick up 1 cubic centimeter of this star stuff that a pulsar is made of, I'd have to exert myself to lift about 1 billion metric tons. They have a number of very interesting phenomena. Their diameter is 10 miles. They rotate rapidly, typically once a second, but they can rotate up to about 1,000 times a second. In that rotation, there is enormous stored energy. My interest in these stars is what makes them go? How do they work? There are a few astronomical objects that have scales of change, if you like, on the order of a human heartbeat. Here's one that plays a program that is about once a second, typically. Some of the most exotic physical conditions in the universe. They have the strong gravity, they have enormous electric potentials. I mean, lightning on Earth is piddling compared to what a pulsar can generate. The magnetic fields on a pulsar are a million times bigger than the Earth's magnetic field. So you put all of those three things together, and you have physical conditions that couldn't be generated for a millisecond in any physical laboratory. So we try to understand how they work, and we also try to understand our basic understanding of physics.